Right. So we're going to start talking today about chemical equations. And when I say balanced chemical equation, it's kind of synonymous with me saying balanced chemical reaction. Okay. So chemical equations, chemical reactions, same idea for me. All right. So first off, chemical equations have two main functions. The first function is they tell you the nature of the reactants and products. For example, is a reactant or a product solid, liquid, gas, or aqueous? Now, the main focus for us will be number two, and that is that chemical equations or chemical reactions, when they're balanced, they tell you the relative numbers of reactants and products. So as an example, right out of the gate here, the combustion of methane gas. So this is a combustion reaction. It's a carbon-hydrogen compound, in this case methane, CH4, in the presence of oxygen, reacting with that oxygen to make carbon dioxide and water. So the reactants are on the left and the products are written on the right. Now, we have to break the bonds in the reactants and we have to form bonds in the products. And this involves changes in energy. So it says bonds in the reactants are broken and then they're rearranged, and then we have bonds in the products being formed. You'll notice that the number of atoms on the left and the number of atoms on the right, the number and types, they all have to be accounted for. So we're going to have to end up balancing this reaction for methane in the presence of O2 yielding CO2 and water. We have to balance this. The law of conservation of mass requires that we balance this. So it says all atoms are present in the reactants must be accounted for in the products. And to do this, we have to balance the equation. Okay, so on top of page 2 of our notes here, I'm going to rewrite that equation. So we have CH4 plus O2 yields or produces CO2 plus H2O. All right, so the first thing I notice is that the oxygens are all over the place. So my carbons match, and I want to give myself two waters, and then I add up all the O's on the right, and I realize I need to put a coefficient 2 in front of the oxygen, the O2. All right, we're going to go over all the rules in detail in just a second, but this is just a quick synopsis of how balancing reactions go. So it says H's and O's were not balanced, and then because O's, or the oxygens, were present in more reagents, it was easier to first balance the H's. So what I did was I saw the H2O, I saw the CH4, I put a big old 2, by big old 2, I mean it's called a coefficient, and then I balanced the oxygens last. So what exactly did I do? What's the process for what I just did? Well, that's what we're going to talk about right now. Some rules. There's only 2 rules, but rule 2 has an A, B, and C. So balancing chemical equations, in other words, balancing chemical reactions. The rules. First rule is an absolute must. You have to write the correct unbalanced reaction. That means you have to know all the formulas. Okay? This is why we work so hard on naming compounds. Given the formula, what's the name of the compound? Given the name of the compound, what's the formula? This is why we spent so much time trying to learn all that stuff. Number 1, write the correct unbalanced reaction, making sure all the formulas are correct. And then once you have that down, you're never going to change the formulas. Rule number 2, balance the equation by adding coefficients. These are kind of large whole numbers. By large, I mean they're larger than the subscripts within the formulas. So balance the equation by adding coefficients in front of the proper formula or formulas. Okay, so A, first thing we would do is you can balance sometimes just by inspection, just by looking at the reaction if it's simple enough. B suggests that we leave the hydrogens and oxygens until the end. And this is because they show up in so many of the compounds, okay? They're not always saved until the end, but by and large, we want to leave hydrogens and oxygens till the end if we can, all right? And then subset of rule number 2, letter C, keep polyatomic ions grouped together. Remember that big list of polyatomic ions? sulfate, SO4 2-, carbonate, CO3 2-, nitrate, NO3-, phosphate, PO4 3-. We want to leave these guys as chunks. So in this example, Na2CO3, that's not 1 carbon and 3 oxygens. Okay, that's, well, we have the NAs. That's 2 NAs plus, and then 1 chunk of CO3 2-. Okay, it's 1 chunk of carbonate that we would have to balance on the left and on the right. All right, so let's get into some examples, and I'm also going to name the type of reaction as I do it. All right, balance the following chemical equations. Now, if you ever see an S, it means a solid. If I ever happen to write L, it's a liquid. AQ is aqueous, and G is gas. And those are usually in parentheses at the end of the formula. So, for example, this is solid copper plus silver nitrate yields silver metal, solid, plus aqueous copper 2, copper Roman numeral 2, nitrate. Remember how we learned how to name stuff? All right, so this is actually a single replacement reaction. Copper is coming in and singly replacing Ag and taking nitrate for himself. So I balance my 2 nitrates on the right with a coefficient 2 on the left. All right, B, this is calcium hydroxide plus H3PO4, which is phosphoric acid. It yields water and calcium phosphate. Now, I'm going to go ahead and rewrite H2O before I balance this. Why am I going to do that? You don't always do it, but I see an OH, a hydroxide on the left. It's generally easier if I split my H2O up into H parentheses OH. So I'm going to rewrite that after I finish this blurb here, which says, when H2O is on the opposite side of hydroxide ion, OH-, it's much easier to rewrite H2O as HOH. So here I'm just going to rewrite it. I'm not going to balance it yet. That's next. CaOH2 plus H3PO4 yields H parentheses OH plus Ca3PO4. I have 4 things to balance here. Okay, that's not 1 P and 4 O's. That's a phosphate chunk. All right, so this hydrogen is part of hydroxide ion. So we're talking about the when we have the OH on the left-hand side of the equation, and I'm going to write the balance equation again. But the H is part of hydroxide, so it's not counted as a lone hydrogen when you're balancing. All right, so what I have is I have CaOH2 plus H3PO4, and I technically have, quote, no hydrogens no hydrogens in my CaOH2, but I do have 2 hydroxides. So I have 4 things to balance. I see I have 3 Cas on the right, put a 3 coefficient. That gives me 6 OHs, put a 6 in front of the HOH. Gave me 6 H's. I go and put a 2 in front of the H3PO4, and usually the last one checks out. If it's taking longer than 3 to 5 minutes to balance the equation, you should erase everything and start again because you're going down the wrong path. This is called a double replacement reaction. You'll see that the first 2 terms, the Ca and the H, are going to doubly replace each other. Ca now goes with the other anion, PO4, while the H now goes with the OH. That's a double replacement reaction. This reaction is a synthesis reaction. Your book calls it a composition. This is 2 things becoming 1. 2 things becoming something that's more sophisticated is a composition reaction. And the S's were more difficult, so I chose to balance them first. 3 and 8, I have to use an 8 and a 3. And then the 16 Cr comes at the end. You'll notice I cannot reduce 16, 3, and 8 in C. My coefficients, there was no way to reduce those, otherwise I could, and I should. D, this is where naming is so important because we're not given formulas, we're given a word equation. Sodium bicarbonate, what the heck is that? Do you know the formula? I hope so. That's from chapter 6, remember? Sodium bicarbonate, in the presence of heat, decomposes to sodium carbonate, carbon dioxide, and water. So most of us can draw carbon dioxide and water, but what is sodium bicarbonate and what is sodium carbonate? All right, this is why naming was so important in the last chapter. In the presence of heat, I would tell you that it's just a little triangle above the reaction arrow. We don't need to worry about that at this point. So it says, first, convert this word equation to a formula equation. That makes intuitive sense. So sodium bicarbonate is NaHCO3. It's decomposing. This is a decomposition reaction. It decomposes to Na2CO3, that's sodium carbonate, plus CO2 plus water. Decomposition reactions, when one thing breaks down into two or more less sophisticated formulas. All right, top of the page, and we're going to continue. Two NAs on the right, I put a coefficient 2. Notice I don't change the formulas, I'm just using coefficients. All I needed to do here was put a 2 on the far left. Now, I did not consider HCO3 a bicarbonate chunk and CO3 a carbonate chunk because I don't see them on both sides, right? E, AU2S3 plus H2 yields AU plus H2S. You can see that the H is coming in, kicking out AU and taking S for himself. This is a single replacement reaction. This one's a fairly straightforward one to balance. So we have AU2S3 plus 3H2 yields 2AU plus 3H2S. I didn't have to screw with the formulas. I'm not even allowed to screw with the formulas. This is a combustion reaction. So F is FC12H22O11 plus O2 yields CO2 and water. Combustion reaction, right? Now the O's are in several places. In fact, they're in everybody. Everybody has at least one O. So I'm going to save those. Okay. What I do see is I have 12 carbons on the left and only one carbon on the right. So I might start by balancing carbon. So C12H22O11 plus O2 yields 12 CO2 plus H2O. And I recognize, so I balance the H's as well, right? So I have 22 H's on the left. That means I have to put a coefficient 11 in front of H2O. Now let me add up all the oxygens on the right. 24 O's in CO2, 11 O's in H2O. That's 35 oxygens on the right, but 11 of them are already buttoned up in the form of C12H22O11. I have to make 24 oxygens out of my O2. So let's put the coefficient 12 in there at the very end. So at the very end, I have C12H22O11 plus 12O2 yields 12 CO2 plus 11 H2O, and that's a combustion reaction. Okay, I did the carbons, then I did the hydrogens, then the oxygens. And that's the usual process for a combustion reaction. All right, G, I see two things combining to form one. This is a combination reaction, also known as a synthesis. Oxygens are in more places than iron, so I balance the iron first. And then I have to put a 1/2 O2 in order to make this work. Now, clearly that's temporary, and it is. So I got there, it's balanced, but I have to multiply this entire thing through by 2, because I can't leave it 2FeO plus 1/2 O2 yields Fe2O3. I have to have whole number coefficients. So if I multiply everything through by 2, talking about multiplying the coefficients through, I have 4FeO plus O2 yields 2Fe2O3. So this is balanced. I cannot reduce the coefficients moving left to right of 4, 1, 2, so this is done. All right, example. Is the following chemical reaction properly balanced? 8Fe plus 6O2 yields 4Fe2O3. Well, if you add everything up, it's balanced. But look at the 8, the 6, and the 4. I can reduce these, right? And when I say I can reduce these, I mean the 8, the 6, and the 4 are all divisible by 2. I can move the coefficients to lower numbers and get the proper balanced equation. So this is going to be 4Fe plus 3O2 yields 2Fe2O3. Okay, everything's balanced, check, and 432 cannot be reduced, check. All right.